Okay students, I hope you are all well and healthy and ready to learn new things. So my name is Palak Patel. I'm working in the Mahatma Gandhi Institute of Technical Education and Research Center Navsari in Civil Engineering Department. I am going to teach you the subject is design of structures. So in this subject we are going to learn two-way continuous slab. So be ready and good luck. The example which we discussed in the previous lecture. Same example here. In a previous lecture we completed S1 slab design, one way continuous slab, and in this lecture we will design S2. Okay, how to design S2? So let's start. Okay, this is a typical floor plan. These are the solution. One way slab with a typical floor level. This is completed. One way slab. We complete one way slab design. One way continuous slab. But in this this lecture, we will complete two way continuous slab. One short is discontinuous. Effective span is calculated. Load calculation is completed. Bending moment calculation. I explain everything in the details. Okay, at B design, one way slab design is complete. Distribution still also completed. Right now we will start from the design of two-way slab. Design of two-way slab. So how we can define this is H2 is two-way. So simply Ly by Lx. Ly means longer span, Lx means shorter span. Ly by Lx ratio, Ly is 6, Lx is 4. Okay, Ly is 6. Okay. Ly is 6 and Lx is 4. Okay, so x by 4 is 1.5, so ratio is less than 2. Ratio is less than 2, so design the slab is two-way slab. Okay, and the first thing we have to find out effective depth, effective span. Or when we design a slab, all the time you just need to find out effective depth and effective span. So first, effective depth. Here is a short span. Short span is 4 meter. 6 is the longer span and 4 is the shorter span. So short span is 4 meter. Is less than 3.5. It's less than 3.5 meter. Okay, and the live load is 4, is greater than 3, is greater than 3. So in this condition we have to follow this effective depth. L by D is equal to 26 into MF. These are the both conditions. Short span is greater than 3.5 and live load is greater than 3. At this two condition is fulfilled, we have to follow this effective depth ratio. Length by depth ratio is equal to 26 into MF. Okay, and if this condition not fulfilled, means shorter span is less than 3.5 or live load is less than 3, at that time we have to multiply this 26 into MF multiply by 0.8. Okay, next assume PT assume कर रहे हैं हम, percentage still will be assume 0.3%. MF modification factor 1.5. I explain all things in the detail. How can we find out MF? Okay, I will never do it repeat these things. You will understand easily how we'll find out MF modification factor from the IS code IS 456 2000 page number 38. There is a graph which is give the modification factor percentage of steel and one MFS graph. You can calculate easily. MF 1.5. Then after length by depth. Length by depth ratio, same equation is here. We have to find out 4000. Sorry, 4000 divided by effective depth is equal to 26 into MF. MF 1.5 is given. MF 1.5 is given. At that time we can find out D. 4000 divided by D effective depth is equal to 26 into MF. So you can find out D effective depth 102.56. 102.56. So we can provide D is 101 110 mm. 110 mm. These are the effective depth which we provide. Okay, then we can find out overall depth. Overall depth, effective depth plus 5 by 2 plus 20. Effective depth plus 5 by 2 plus 20. So we can find out the depth of the slab. Next we have to find out effective span. Effective span, first is the shortest span. In a one-way slab we have to find out only effective span into one direction for the one-way slab, but in a two-way slab we have to find out effective span at both directions. This is the one-way slab. This is two-way slab. So you can see that we can find out effective depth only one direction here. Only for the one direction here, effective span. But for the two-way slab, we have to find out effective span in the both direction, Ly and Lx, for the both. Okay. So first of all, for the shortest span means for the Lx, width of support is 230 mm, which is given. Width of support is 230 mm, which is given. We have to find out clear span. Clear span 4000 minus 230. 230 means effective width of support. 4000 minus width of support. So clear span is 3770 mm. 3770 mm. These are the clear span which shortest spans. Clear span for the shortest span. Okay. Now this is the continuous slab, so we have to follow IS 456 2000 page number 34. IS 456 2000 page number 34. Same condition we discussed earlier. If continuous slab, in a case of continuous beam or slab, if the width of the support is less than 1/12 of clear span, the effective span shall be in 22.2a. Okay, this given. So first condition is here, clear span divided by 12. Clear span divided by 12. If this value, clear span divided by 12, this value is lesser than width of support, we have to follow code number 22.2a. Clause number 22.a. clear span divided by 12, clear span 3770, clear span 3770 divided by 12, 314.16 mm. Okay, these are the greater than width of support. What we need? We need the lesser than. Width of support is less than clear span divided by 12. Okay, so we have to follow IS code 22.2a. Code 22.2a here. A simply supported beam or slab, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective width depth ratio or beam or a center to center of supports, whichever is less. So in the 22.a we get two conditions here. First, clear span plus effective depth. Clear span is summation with effective depth. Okay, and second is center to center of support. So by this two value, whichever is less, we can use this at a first clear span plus effective depth 3770 plus 110. So clear span is 3880 mm. 3880 mm. Second, center to center of support. Center of support is 4000 mm is given. So whichever is less, we take it as a clear span. So for the LX, 3880 mm as a effective span for the shorter span. Same formula will be used for the LY, means longer span. LY means longer span. LY is equal to 5880 mm. Okay. Now we have the effective span, effective depth. We can calculate load calculation. Okay. So first we have to find out self weight of slab. Self weight of slab. How we assume 1 meter strip on a two-way slab. Same condition for the one-way slab. This is the same condition we use for the two-way slab. So self weight of slab 0.135. 0.135 is the effective. Now 0.35 is the thickness. It's the thickness of slab. Look at here. Overall depth 135 mm. Okay. So this overall depth is given 0.135. 1 meter strip into 25. So self weight of slab is 3.375 mm. 3.375 kilonewton per meter square. These are the UDL load. Next, floor finish 1 kilonewton per meter square. Second, live load 4 kilonewton per meter square. This both value is given in the example. Next, total 8.375 kilonewton per meter square. Total load multiply by 1.5. It's a factor load. It's a factor load 1.5 into 8.375. Okay. So this is a factor load. Factor load multiplied by 1.5, we can total factor load is 12.5.6 kilonewton per meter square. Okay, these are the factor load is given. Now we have to find out design moment. Okay, for the find out moment, we have to follow IS 456 page number 91 table 26. IS 456 page number 91. Page number 91, table 26. Bending moment coefficient for the rectangular panel supported on the four side with a provision for a torsion at corners. Supported on four side. So these are the coefficient, bending moment coefficient for the two-way slab. Okay. So first we need a shortest span coefficient, and this is the longest span coefficient. Okay. And we need Ly by Lx value. We need Ly by Lx value. What is Ly by Lx value? Longest span means shortest span. Effective span 5.88 divided by 3.88. Ly by Lx 1.52. Ly by Lx ratio is 1.52. So I can assume Ly by Lx ratio is 1.5. Is 1.5. Okay. Now we have to follow this 8 column for the find out effective depth. Find out coefficient of bending moment. Okay. But here is one condition, type of panel and moment considered. So we have to check out this. So first is interior panel. One short edge discontinuous, one long edge discontinuous, two adjacent edge discontinuous, two short edge discontinuous. So first let's check out the condition of the S2. S2 is, here is a four sides. Okay, it's 4 meter, it's 6 meter, here is also 4 meter, here is also 6 meter. Okay, so this S2 is not an interior panel. Okay, all edges are not continuous, only one edge is discontinuous. Which one? Shorter edge. Okay, this slab is called as interior panel S3. S3 called as interior panel. Okay, and what, but we design S2 here. So S2 one short edge means this is 4 meter. This short edge is discontinuous. Okay, so let's check this condition here. Here second, one short edge discontinuous, negative moment at a continuous edge and positive moment at a mid span. Negative moment at a continuous edge and positive moment at a mid span is 1.5. 8 column we have to follow, and one short edge discontinuous the point 0.057 and positive moment 0.044. Okay, so this condition is given. So let's draw some figure for the S2. Here is S2 slab for the alpha X and alpha Y. Okay, first we discuss about alpha X. Look at here, short span coefficient alpha X. Here is a figure, alpha X in the X direction. So let's check alpha X. So this direction, this is also alpha X, this is also alpha X. What is given? Negative moment at continuous edge 0.057, negative moment at continuous edge. So these are continuous edge. So here is a negative moment 0.057. Same here, minus 0.057, negative moment. Second, positive moment at mid span. Positive moment at mid span 0.044. So at a mid span we have a positive moment plus 0.044. So this is the alpha X, and here alpha Y. alpha y. Two condition here, alpha x and alpha y. So for the alpha y, we have to follow this 11 number column. Same condition, negative moment at continuous edge 0.037 and positive moment at mid span 0.028, 0.037 plus 0.028. So these are the middle span moment. These are edge strip. So this alpha y did not here because this slab is discontinuous. This span is discontinuous, but this span is continuous. Okay. So that's why, look at here, alpha x and alpha y. Both value we have. Okay. For the mx positive at a support, alpha x WLX square. These are the equations for the find out the moment. Coefficient into weight into span whole square, Lx whole square. Okay. So mx is equal to 0.445, alpha x is equal to 0.045, w is equal to 12.56, factor load which we calculate, Lx 3.88 whole square. So mx is 8.50 kilonewton, where mx is at positive, so means this positive means at the mid span. Alpha x is positive, so mx positive will be at mid span. Okay. Second, for the negative, alpha x WLX square, alpha x WLX square. So alpha x negative is 0.58, w 12.56, lx 3.88 square. So mx is minus 10.96 kilonewton into meter. So these are the mx negative at the support, mx negative at the support. Same for the my, alpha y WLY square. Okay. 0.228, w 12.56. Here is lx 3.88 square. So my is 5.29 kilonewton into meter, 5.29 kilonewton into meter. So this is my at the mid span. Mx negative, we can find out mx negative. Now we have to design the reinforcement along lx. Along lx means shorter span. We have to use mx positive, which is at the center, which is at the center of slab. So mx plus 8.50 kilonewton into meter. So effective depth is 110 mm. Effective depth is 110 mm. mu upon bd square. Mu upon bd square, we have find out this 8.50 into 10 raised to 6 divide by 1000 into effective depth 110 whole square, 110 square. These are the mu upon bd square. By the mu upon bd square, we can find out pt from the sp 60.223, 0.203. So from the pt ast we can find out 203 divided by 100 into 1000 into 110. So ast is 223.30 mm square. Okay. Provide 8 mm diameter bar at 220 mm center to center along lx. So lx design is completed, means shorter span design is completed. 8 mm diameter bar at 220 mm center to center. This design is completed. Next design for the along ly. Ly we use my, moment at a y direction, effective depth at the y direction. 110 minus 8, 8 means diameter of bar we have neglected. So effective depth at a longer span is 102 mm. 102 mm. Find out mu upon bd square. 5.29 into 10 raised to 6 divide by 1000 into 102 square. So mu upon bd square is 0.508. 0.508. Find pt 0.145 from the is sp60 page number 37. Okay, next ast. So area of steel is 147.90 mm square. This is along ly direction. So 8 mm diameter bar at 300 mm center to center. This is provided. Okay, now we have to design our supports. At the supports, our continuous edge of beam B4 and B7, where at B4 and B7, here is B4 and here is B7. So at this support we have to design. Okay. Mx is x direction moment at direction minus 10.96 kilonewton per kilonewton into meter. Find out mu upon bd square is 0.90. So by the mu upon bd square we can find out pt 0.264 percentage. 0.264 percentage. Capital AST 0.264 divided by 100 into 1000. So AST is 290.4 mm. 290.4 mm. And then after provided 8 mm diameter at 170 mm center to center at top our beam B4 and B7. Okay, extend this steel for L by 4 distance on either side of center of supports. So these are the one at support completed design. And next, over continuous edge of beam B90, where B4 and B7 design completed, we have to design B90. For the B90 we have to use My negative, My minus 0.7. So mu upon bd square 0.578, pt 0.172, capital AST 0.172 divided by 100 into 1000 into 110. So AST is 100. AST is 189.2 mm square. So provide 8 mm diameter at 260 mm center to center. Okay, at beam 90. Reinforcement at in edge strips. What is edge strip? What is edge strip? So edge strip is look like this. See here. It's your slab. It's your slab. At the middle, we assume 1 meter strip. Okay. So this is called middle strip. And from the edges, though this is called edge strip. This both. Edge strip is not as a beam here. It's interior of the slab. Okay. Your beam is here. Okay. Here is your beam. From the beam, the interior of the slab, this is called edge strip. Okay. So we are going to design edge strip here. So for the edge strip, minimum percentage of steel is 0.12 percentage. So AST minimum 0.12 divided by 100 into 1000 into 135. So AST 162 mm square. provide 8 mm diameter at 300 mm center to center. Okay, these are the edge strip design is completed. Next, torsion reinforcement at corners. We need a torsion reinforcement at a corner for resist torsion moment. Right now we can find out torsion reinforcement corner from the page number 90 IS 456. It's 91. Look at here. Torsion reinforcement shall be provided at any corners where the slab is simply supported on both edges meeting at that corner. It shall be consist of top and bottom reinforcement, each with a layer of bars placed parallel to the sides of the slab and extending from the edge a minimum distance of 1/5 of the solder span. Okay, 1/5 of the solder span. Length is 1/5, means Lx by 5. It's the length of torsion reinforcement. Next, the area of reinforcement in each of these 4 layers shall be 3/4, means 3 by 4. 3 by 4 of the area required for the maximum mid span moment in the slab. Maximum mid span moment in the slab. So maximum mid, in the mid we want 228 mm square steel is required. So by this condition we have to reinforcement in each 4 layer 3 by 4 into 228, so 171 mm square. 171 mm square reinforcement area is required. Reinforcement area is required. So AST in each layer at a corner when one edge is discontinuous. When one edge is discontinuous. So 0.50 into 171 into 85.50 mm square. These are the area. These are the area where one edge is discontinuous. We need 0.5, 50%. Here. Torsion reinforcement equal to the half that described in divide shall be provided at the corner contained by edges over only one of which the slab is discontinuous. Half of the described means d by 80, we describe 3 by 4 of the area required for the middle span. Okay, area required for the middle span in clause number D 1.8. Okay, this described in the D 1.8, but D 1.9 what said? They said reinforcement equal, torsion reinforcement equal to the half that described in D 1.8. Means described D 1.8 is 3 by 4 of area of reinforcement. Okay, and this value is equal to half of that described, means 3 by 4 into area of reinforcement divided by 2. So these are the reinforcement area required for the torsion reinforcement. Okay, so length of bar Lx by 5. I told this span is shorter span by 5. Lx by 5 is 3880 divided by 5. So length of bar is 780 mm. 780 mm. Okay. So provide two numbers of 8 mm diameter bar of 4 layers at corners near C5 and C9. Numbers we find out means capital AST divided by small AST. 8 mm diameter bar area is 50. 8 mm diameter bar, small AST means cross section area of 8 mm diameter bar is 50 mm. So we required 4 numbers of bar in each 4 layers at corners near columns C5 and C9. Okay. And at the near corner C6 and C10, no torsion reinforcement is required. Means at a C6 and C10, no torsion reinforcement is required. Look at here. We provide torsion reinforcement at C5 and C9. But at C6 and C10, no torsion reinforcement is required here. Okay. So our only torsion reinforcement at two corners, C5 and C9. Here is a figure of two-way reinforcement. Two-way slab, 8 mm diameter bar at 70 mm center to center. 8 mm diameter bar at 220 mm center to center along LX. 8 mm diameter bar at 300 mm center to center along LY. Okay. Now this graph draw. This is the two-way slab. Okay. So this span is 8 mm diameter at 220 mm center to center along LX and here 8 mm diameter bar at 300 mm center to center along LY. Okay. Here is 8 mm diameter bar at 270 mm center to center. Okay, these are the at the support. Great. Then after here is effective depth 135 mm overall depth, effective depth 110 mm. Here is a clear span along Alex. Okay, 3880 mm. Clear span is given. Okay, these are the cross section of slab with reinforcement detailing. So our slab design is completed. So in this lecture we complete design S2. Both slab is completed. ST is interior panel. No need to. You can practice this S3 for the design. Just change in the coefficient. Just change in the coefficient of the bending moment. Okay. If you want to design S3, just try by yourself. Practice it, and you will become great for the structure design. Okay. If any question and query, you can ask me or comment me. I give reply as soon as possible. Okay. So in the next lecture, we will design a continuous beam and then after column and foundation. So we will meet soon as possible. Take care and bye.